Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Health Sciences, SOHS, Bachelor's degree programs, Post-Basic Bachelor of Science in Nursing B.Sc.N. PB, BNS-102 Applied Sciences, Biochemistry, Biophysics, Microbiology and Nutrition and Dietetics, Block-1 Biochemistry, Unit-1 Biochemistry, Basic Concepts. 1.0 Objectives. After reading and understanding the unit, you should be able to fill circle define biochemistry and state its importance for nurses. Fill circle explain the three physical states of matter and their interconversion. Fill circle differentiate between the physical and chemical changes of matter. Fill circle classify matter and list the differences between compounds and mixtures. Fill circle describe different types of chemical reactions, with suitable examples. Fill circle draw structures of various atoms. Fill circle discuss the two types of chemical bonding and illustrate with examples, and fill circle list the applications of various radioisotopes in the field of medicine. 1.1 Introduction. This is the first unit in this block of biochemistry. In this unit, you will be introduced to the subject of chemistry and biochemistry and its importance in our day-to-day life and also in the field of nursing. The unit will mainly deal with some of the basic concepts in the study of chemistry and biochemistry and their applications. In this unit, we shall study the aspects related to physical and chemical changes, about the structure of atom and chemical bonding. There will be a brief discussion on isotopes and their applications in the field of medicine. Biochemistry deals with the study of the chemistry of living organisms. In this branch of chemistry, we learn about the chemical compounds that make up the living systems and the changes they undergo during the life process. In this block, you will be learning some of the basic concepts in chemistry in Units 1 and 2. Units 3 to 6 tell you about the applications of chemicals and chemical principles in the living system. 1.2 Significance of biochemistry in nursing. Why should you study chemistry or biochemistry at all? Does it have any relevance to nursing profession? These are questions for which you would like to get the answers. Biochemistry is concerned with composition, characterization and transformation of matter. As nurses, your day might begin by taking the temperature of a patient, or giving him, her a dose of a medicine, or administering an intravenous drip of saline or glucose, or it could also be choosing a proper diet for the patient's first meal. While giving the drip, it is advantageous for you to know the correct strength or concentration of the solution. Similarly, a knowledge of the components of food and their correct proportions enables you to choose and advise a balanced diet for the patient under different situations. Thus, if you strengthen your knowledge regarding the nature of chemical substances and their importance in daily lives, you can develop proper skills in the care of your patients. 1.3 Matter and its properties. You have just learnt about the significance of learning biochemistry. One of the study area is matter. Now, how do we define matter? Matter is any object, living or non-living, that has mass and occupies space. Matter ranges from the tiniest dust particle to a huge mountain, or from a single small cell to a complete human being. In this block, you will learn about the composition, classification, structure, properties and behavior of matter. Mass refers to the amount of matter contained in any object. 1.3.1 Physical states of matter. We are surrounded by matter of one kind or the other. In fact, our body itself is composed of matter. Our atmospheric air consists of oxygen, nitrogen, carbon dioxide etc., which are all gases. The components of our food, such as rice, wheat, sugar and salt, building materials, such as sand, cement, iron, wood, etc., are all solids. Water, milk, coffee, tea, etc., are all liquids. Thus, we can say that matter exists in three fundamental states as solids, liquids and gases. These are the three physical states in which any type of matter exists. However, a very important fact that we must remember is that any type of matter can exist in all or any of these three physical states under different conditions. How is this possible? In order to understand this fact, let us look at the arrangement of matter in these states. All forms of matter are made up of tiny units or particles. Depending on how closely or loosely these particles are packed and their mobility, matter exists as a solid, liquid or gas. Solids. When particles in matter are very tightly and closely packed together, they remain fixed in their positions with least movement. This gives a definite size, in terms of volume, and shape to the matter, and it exists as a solid. Examples are wood, iron, salt, sugar, etc. Liquids. In liquids, the particles are more free to move about since they are packed together not as tightly as in a solid. Thus, liquids do not possess any fixed shape, but take the shape of the container in which they are kept. However, like solids, liquids also have a definite volume. Examples are water, milk, blood, mercury, etc. Gases. Gases have no shape or fixed boundaries and fill completely the volume of any container. This is due to separation of particles from each other by large empty space, giving them scope to move about very freely. Examples are oxygen, carbon dioxide, hydrogen, helium, etc. Fig. 1.1 depicts the packing of particles in the solid, liquid and gaseous states. In solid state, there is orderly arrangement of particles. In liquid state, the arrangement is partially orderly. In gaseous state, there is random and disorderly arrangement of particles. Figure 1.1. Packing of particles in different physical states of matter. Look at the screen. When we say a particular matter is solid, liquid or gas, we refer to the state in which that matter exists at ordinary temperature and atmospheric pressure. By altering these conditions, we can bring about a change in the nature of packing of the particles in the matter. Thus, by suitably altering temperature and pressure, we can change the matter from one physical state to another. A familiar example would be that of water existing in solid, liquid and vapor states, see Fig. 1.2. Figure 1.2. Interconvertible states of matter. Look at the screen. 1.3.2 Physical and chemical changes. We know from our experience that we can distinguish different types of matter by observing their special features or characteristics. Such features are called properties of matter. From a study of the properties of matter, we can also identify a particular type of matter. Matter is capable of undergoing two types of changes, namely, the physical change and the chemical change. Physical changes. Matter may undergo changes in its size, shape and physical state. For example, a large piece of wood can be cut into several smaller pieces. Ice melts and becomes a liquid on warming. On further heating, water is converted to steam. Measurements such as density, freezing point, boiling point, etc. help in the correct identification of the matter. For example, ice and camphor melt at specific temperature which are quite distinct. Yet, in all such physical changes, the chemical composition of matter remains same. Physical changes do not involve changes in the composition of matter. Chemical changes. Chemical changes are associated with changes in the structure and composition of matter. When we burn a piece of wood in air, it produces light and heat. At the same time, the material making up wood disappears, producing smoke, carbon dioxide, a chemical equation gives the complete details regarding the nature of changes in the composition of original matter. Products and examples of chemical changes to bring about the reaction cooking itself. Of food, curdling of milk, boiling of number of molecules of each reacting element or compound and also the number rusting of iron molecules of the product form. 1.3 chemical equation so represented compounds and has to be balanced. We can simplify the study of matter by classifying it into reactants as exactly balanced matter can be classified as follows. See Fig. In order to represent chemical equations, Figure 1. We use the symbols of classification of matter. Look at compounds are represented by their formula. An element is a formula of a compound shows atoms with the same atomic number of atoms of each element present in a molecule of form of substances and can have stable reactions are of several types. They cannot be further. We shall know about them into any simpler form by ordinary chemical or simple combination. They are like the bricks. This reaction involves the building of more complex substances. Each and every type of matter, living or non-living, is built H22 HCl. These bricks chlorine gas till now at least 108 elements have been discovered and more are likely Cow plus
to be
H2O
discovered in
equals
future.
calcium hydroxide.
Of these 108
calcium
elements,
oxide
only the
plus
first 92 are
water
naturally
equals
occurring,
calcium hydroxide,
while the rest
2.
are artificially
Simple
prepared.
decomposition.
Classification
It is a reversal
and
of the
properties
above
of
reactions,
elements,
wherein
elements
a complex
occur in
molecule
different
breaks
physical
down
states.
or near about 30
Decomposes
degrees
into
Celsius.
simpler substances.
Most elements are
2
solids.
HGO
A.
equals 2 Hg
Few are
plus
gases and
O2.
only 5 elements
Mercuric
exist as
oxide
liquids.
equals
Mercury
circle
metal
solid
plus
oxygen,
copper, iron,
3
silver,
displacement,
gold,
carbon,
in this reaction,
sulfur,
an
etc.
element displaces one
Filled
constituent
circle
from a
liquids,
compound,
mercury,
setting it free,
bromine,
and
etc.
itself
Filled
unites with
circle
the
gases,
other or remaining
oxygen,
constituents
hydrogen,
forming a compound.
nitrogen,
2HCl
neon,
plus
etc.
zinc arrow zinc chloride plus
Elements
H2.
can be classified into 3
hydrochloric
groups.
acid
Filled
plus
circle
zinc
metals,
arrow
filled
zinc
circle
chloride.
non-metals.
Here zinc has
Filled
displaced
circle rare
hydrogen
gases.
from HCl,
We shall
releasing
now
it as
list the
hydrogen
properties
gas.
of metals and non-metals for a
double
comparison.
decomposition.
When
Metals.
two different
Metals
compounds
are
react with
characterized
each
by a
other,
set of
there is a
physical
simultaneous
properties which are given
displacement
below.
of components in both
Filled circle
producing
luster,
two new compounds.
an ability to take high polish
Sodium
and shine.
chloride plus silver 1
Filled
nitrate
circle
arrow
malleability,
sodium nitrate
an
plus
ability to
silver
get
1
transferred
chloride.
into thin sheets
Sodium
on beating or
chloride
pounding.
plus silver nitrate
Filled circle
arrow
ductility,
sodium nitrate
capable of being
plus
drawn into
silver
a thin
chloride.
wire.
Filled
Note,
circle
when
hardness,
representing chemical
resistance toward
equations,
being
for the
scratched
sake
by
of
other
convenience,
substances,
we usually
filled circle physical
write
state
the reacting
at ordinary
molecules on the
temperature,
left side
30
and the
degrees
product
Celsius.
molecules on
Most
the right.
metals are solids.
The
Arrow
filled
in
circle
between
conductivity,
shows the direction
ability
of reaction.
to transfer heat or electricity.
Non-metals. Non-metals differ from metals in the following respects. They are filled circle lusterless, filled circle non-malleable, filled circle non-ductile, filled circle soft. White phosphorus on slight warming becomes soft. Sulfur is an yellow powder. Filled circle poor conductor of heat or electricity. An exception is graphite, a form of carbon, which is a good conductor of electricity. Filled circle mostly solids or gases at room temperature, 25 degrees Celsius. Rare gases. Gases such as neon, helium, argon, etc. are called rare or inert or noble gases. These are generally incapable of taking part in chemical reactions. Names of elements and their chemical symbols. The following table, Table 1.1, lists some of the more common elements, with their common names, names of Latin, Greek origin, in brackets, and their symbols. Table 1.1, names of some elements and their symbols. Look at the screen. A chemical equation gives the complete details regarding the nature of reactants, nature of products and also conditions needed to bring about the reaction itself. It also specifies the number of molecules of each reacting element or compound and also the number of molecules of the product formed. A chemical equation so represented has to be a balanced equation, so that the number and type of atoms in reactants is exactly balanced by those present in the products. In order to represent chemical equations, we use the symbols of elements, while compounds are represented by their formulae. The formula of a compound shows the type and number of atoms of each element present in a molecule of the compound. Chemical reactions are of several types. We shall know about the major ones. 1. Synthesis or simple combination. This reaction involves the building of more complex substances from simpler ones. Cl2 plus H22 HCl. Chlorine gas plus hydrogen gas equals hydrogen chloride gas. Cow plus H2O equals calcium hydroxide. Calcium oxide plus water equals calcium hydroxide. 2. Simple decomposition. It is a reversal of the above reaction, wherein a complex molecule breaks down or decomposes into simpler substances. 2HGO equals 2Hg plus O2. Mercuric oxide equals mercury metal plus oxygen. 3. Displacement. In this reaction, an element displaces one constituent from a compound, setting it free, and itself unites with the other or remaining constituents forming a compound. 2HCl plus zinc arrow zinc chloride plus H2. Hydrochloric acid plus zinc arrow zinc chloride. Here zinc has displaced hydrogen from HCl, releasing it as hydrogen gas. 4. Double decomposition. When two different compounds react with each other, there is a simultaneous displacement of components in both, producing two new compounds. Sodium chloride plus silver 1 nitrate arrow sodium nitrate plus silver 1 chloride. Sodium chloride plus silver nitrate arrow sodium nitrate plus silver chloride. Note: when representing chemical equations, for the sake of convenience, we usually write the reacting molecules on the left side and the product molecules on the right. The arrow in between shows the direction of reaction. 5. Oxidation reduction. In very simple terms, we can say that addition of oxygen to a substance or removal of hydrogen from the substance is oxidation. Likewise, addition of hydrogen to a substance or removal of oxygen from it is reduction. Oxidation and reduction occur simultaneously in the same reaction. That is to say that if one substance is oxidized, then the other is reduced. CH4 plus 2O2 arrow CO2 plus 2H2O. Methane, carbon dioxide, water. In this example, methane is oxidized to carbon dioxide, while oxygen is reduced to water. In the above sections, you have learned that matter exists in three physical states and that it can undergo characteristic physical and chemical changes. You have also seen that matter can be classified into elements, compounds and mixtures. Further, you have become aware that elements and compounds take part in chemical reactions in different ways. We are now ready to move on and study the structure of atom and chemical bonding. 1.4 Atom and its structure. Let us remind ourselves that elements are building blocks of all forms of matter. However, elements in turn are made up of smaller units called atoms. Atom is the smallest particle of an element that can take part in a chemical reaction. Atoms, in general, cannot exist independently. An atom has the chemical properties characteristic of an element. When two or more atoms combine with each other, they produce molecules of elements or compounds. We shall look at some examples illustrating this concept. O plus O equals O2. Atom-atom molecule. Similarly, H plus H equals H2. N plus N equals N2. Cl plus Cl equals Cl2. Such elements are said to be diatomic, since each molecule consists of two atoms of the element. But metals and rare gases are monoatomic, since a molecule consists of only one atom of the element. Examples of monoatomic elements are metals and rare gases which are given in table 1.1. Dalton's atomic theory. The English chemist, John Dalton, in the year 1805, put forward a theory to explain certain features of chemical reactions. It says that a. Atoms constitute the minute, indivisible particles of elements. Further, atoms of the same element are exactly alike in mass and chemical properties, but differ from atoms of other elements in these respects. B. Chemical reactions between elements are actually the reactions between the atoms making up the elements. In such reactions, the atoms of different elements combine in simple ratios of whole numbers, that is, chemical reactions occur between definite numbers of atoms of different elements. C. Atoms belonging to different elements possess different mass which is not altered. When atoms undergo chemical reactions, there are as many different types of atoms as there are elements themselves. These atoms differ widely in their size and mass, but all have certain common structural features. So we come to the study of the structure of atoms. What are atoms composed of? 1.4.1 Structure of atom. For a very long time, scientists had thought that the atom represented the ultimate, smallest part of an element and that it was not possible to split it further into smaller bits. But, when finally atoms yielded to splitting by nuclear reactions, the presence of subatomic particles, which were even smaller, were discovered. Let us get to know the nature of these particles and their properties. Atoms of all elements are mainly composed of three types of particles. These are 1. Protons, which have a mass of 1 unit and carry 1 unit of positive electrical charge. 2. Electrons, which possess a negligible mass, roughly 1/1837th of the mass of proton, but carry 1 unit of negative electrical charge. 3. Neutrons, which have a mass of 1 unit, nearly same as that of a proton, but carry no net electrical charge. The following table, Table 1.2, summarizes these features of the subatomic particles. Table 1.2, Properties of subatomic particles. Look at the screen. Atoms of all elements are built of these three types of particles. However, atoms of
Different elements differ in the number and arrangement of subatomic particles. 1.4.2 Atomic number, mass number and atomic mass. Atoms belonging to different elements can easily be distinguished from one another using their atomic numbers and mass numbers. We shall briefly explain both these terms. Atomic number. Atomic number refers to the number of protons or number of electrons in an atom. Atomic number equals number of protons equals number of electrons. The atomic number of the atoms of an element is unique and it acts as an identity for its atoms. Remember that atoms of different elements have different atomic numbers. Example, atomic numbers of H, C, N, O and Cl are 1, 6, 7, 8, and 17 respectively. Mass number. Mass number is the sum of the number of protons and neutrons in an atom. It is always a whole number. Mass number equals number of protons plus number of neutrons. Equals number of electrons plus number of neutrons. For example, mass number of helium equals 2 protons plus 2 neutrons equals 4. Mass number of oxygen equals 8 protons plus 8 neutrons equals 16. The mass numbers and atomic numbers of a few elements are given in Table 1.3. Table 1.3. Composition of atoms of a few elements. Look at the screen. Atomic mass. The atomic mass denotes the actual mass of an atom. Since any atom is composed of protons, electrons and neutrons, its mass is equal to the sum of the masses of all the three particles. But since the mass of electron is negligibly small in comparison to that of proton and neutron, its mass is not taken into account. So we have atomic mass equals mass of protons plus mass of neutrons. For example, atomic masses of H, C, N, O, Cl are 1.008, 12.01, 14.01, 16.00 and 35.45, respectively. Now compare these with the mass numbers of the same elements given in Table 1.3. What do you observe? You find that the atomic mass and mass number of the atoms are nearly same, but not always identical. Atomic masses can be either whole numbers or fractions also. The reason for the fractional value of atomic masses will be explained later. In subsection 1.5.4. 1.4.3 depicting the structure of atoms. Atoms are organized in a very systematic way wherein the subatomic particles are distributed and arranged in a definite pattern. The central portion of the atom is called nucleus, which contains protons and neutrons. The nucleus carries a positive charge that is equal to the number of protons present in the atom. Surrounding the nucleus, the electrons revolve in circular paths at considerable distances. You can imagine atoms to be miniature solar systems, with the electrons encircling the nucleus, just as planets revolve around the Sun in definite orbits. The path traversed by electrons around the nucleus is called orbit or shell. Each shell can accommodate only a definite maximum number of electrons. Different shells are either numbered first, second, third, etc. or designated as K, L, M, N and so on, starting from the shell nearest to the nucleus. The distribution pattern of electrons in different shells is as follows. Look at the screen. An important feature about atoms is that they possess equal number of positive and negative charges. Therefore, their net charge is zero. Atoms are electrically neutral. In order to depict the structure of an atom, we need to know the exact number of protons, neutrons and electrons possessed by it. We can make use of the relationship mentioned earlier. Mass number equals number of protons or number of electrons plus number of neutrons. For example, if an atom has 12 neutrons and has a mass number of 23, its number of protons, or number of electrons, is equal to 23 minus 12 equals 11. Now that you have understood the concept of atomic number, mass number and the procedure for distribution of electrons in different shells, you are equipped to represent the structure of atoms of elements with atomic number up to 18. For representing the structure of atoms with atomic number greater than 18, you have to No more concepts. We are not going to discuss these aspects in this course. Fig. 1.4 on structure of atoms reveals the following. Fill circle the nucleus contains protons and neutrons. Fill circle the simplest atom, hydrogen, has only one proton, but no neutron. Fill circle electrons start occupying the shells, beginning from the one nearest to the nucleus, K shell. Fill circle K shell can take a maximum of 2 electrons. It is complete in the atom of helium. Fill circle from the 3rd to 10th element, the 3rd and subsequent electrons occupy the 2nd shell, L shell. Fill circle from lithium through fluorine, the L shell acquires electrons ranging from 1 to 7. Fill circle with the 10th element neon, the L shell is complete with 8 electrons. Fill circle for elements with atomic number 11 and above, electrons start occupying the 3rd shell, M shell, and onwards, as the K and L shells are already complete with 2 and 8 electrons, respectively. The knowledge of the structure of atoms will help us to understand how atoms combine to form molecules. This brings us to the concept of chemical bonding. Figure 1.4, structure of atoms of the first 10 elements. Look at the screen. Note, circles represent electrons. 1.5 chemical bonding. Why do atoms combine? What type of atoms remain singly and why? Do atoms of all elements have the tendency to combine with atoms of other elements? You may be asking yourself these questions and would like to find suitable answers to them. Generally, atoms do not remain single because in that state they are highly unstable. By combining with atoms of same or different elements, they gain stability. For example, an oxygen atom is not stable enough to remain alone. But it can combine with another atom of oxygen to give a molecule of oxygen, O2, which is quite stable. Also, an atom of oxygen can combine with 2 atoms of hydrogen to form a molecule of water, H2O. As compared to an atom of oxygen or an atom of hydrogen, water molecule is more stable. In this way, atoms of same or different elements combine to attain a state of stability. However, the atoms of rare gases, mentioned in Table 1.1, can remain singly and the number of compounds formed by them are much less. In other words, rare gases are chemically inactive so that these are also known as inert gases. Again, the reason for atoms of rare gases remaining singly and their chemical inertness is to be traced to their stability. We can relate chemical stability of a rare gas to the arrangement of electrons in its atoms. It has been observed that presence of 2 electrons in K shell or 8 electrons in L, M and other shells signifies stability. That K shell can have only 2 electrons is related to its capacity, but in case of shells other than K shell, 8 electron arrangement provides stability to an atom. The chemical bonding, at least in large number of cases, can be explained in terms of the tendency of atoms to attain electronic arrangement corresponding to helium, having 2 electrons in its only one shell, namely K shell, or to any other inert gas, having 8 electrons in its outermost shell. The atoms of elements may attain inert gas electronic structure through gain or loss or sharing of electrons. This is the basis of chemical bonding. To understand this further, you go through the following material. 1.5.1 Valency. In simple terms, valency refers to the combining power of atoms. Look at these 4 compounds carefully. HCl, hydrogen chloride, H2O, water, NH3, ammonia, CH4, methane. You will notice that 1 atom each of Cl, O, N and C have combined with 1, 2, 3 and 4 atoms of H, respectively. From this, we say that the valency of Cl is 1 and that of O, N, and C is 2, 3 and 4, respectively. However, this method cannot be used always, as all compounds do not contain H atoms in them. Thus, in order to find the valency of various atoms, we look for a property that is common to all atoms. This property is the acquiring of electrons to obtain 2 electron structure in K shell or 8 electron structure in any other shell, i.e., inert gas electronic structure. Atom may attain inert gas electronic structure by the following 2 ways. 1. By complete transfer of one or more electrons from the outermost shell of one atom to that of the other. 2. By a process of sharing of pairs of electrons between the outermost shells of two atoms. We shall now give a proper definition for valency as follows. Valency of an element is equal to the number of outer shell electrons that its atom has to gain, lose or share, in order to realize a stable outer shell electronic structure. Transfer or sharing of electrons helps two atoms to unite and from molecules. This process, called chemical bonding, is of two major types, electrovalent bonding and covalent bonding. 1.5.2 Electrovalent bonding, ionic bonding. In this type of bonding, two atoms belonging to different elements transfer one or more outer shell electrons from one to another. Let us suppose that the two atoms are A and B. A donates an electron to B such that both of them attain inert gas electronic structure. Then the following are true. Fill circle both atoms A and B complete their outer shell with 8 electrons. Fill circle to begin with, both atoms A and B are electrically neutral, net charge is 0, since the number of protons, plus weight charge, exactly balance the number of electrons, weight charge, in each. Fill circle atom gains a unit, plus, charge on losing an electron, while atom B acquires a unit charge by accepting an extra electron. Fill circle atom A is changed into a positively charged ion, A+. Whereas, atom B is changed into a negatively charged ion, B. Fill circle A+, is called a cation and B is called an anion. Fill circle due to the opposite charges on them, ion A+ combines with ion B to form a compound AB. The type of bonding is known electrovalent bonding. The compound formed is called an electrovalent or ionic compound. The formation of sodium chloride, from an atom of sodium, Na, and an atom of chlorine, Cl, can be taken as an example for showing electrovalent bonding. The numbers within brackets after each atom in the following example refers to the arrangement of electrons in K, L, M, etc. shells. Na, 2, 8, 1, plus Cl, 2, 8, 7, Na plus, 2, 8, plus arrow Cl, 2, 8, 8. Note that both Na plus and Cl icons have 8 electrons in their outermost shell, which represents inert gas electronic arrangement. Other examples: potassium chloride, KCl, sodium bromide, etc. 1.5.3 Covalent bonding. It is interesting to know that with some atoms transfer of electrons is not possible to gain stability. Hence, they share pairs of electrons between them. When this happens, the shared pair of electrons belongs to both the atoms. The two atoms then combine with each other to form a molecule through covalent bonding. Some of the features of covalent bonding are as follows. Fill circle: the combining atoms may belong to the same element or different elements. Fill circle: more than one pair of electrons may be shared by the concave atoms. Presence of 1, 2 and 3 pairs of electrons between two atoms led to single, double and triple bond, respectively. Fill circle: the process of sharing electrons does not produce ions, charged particles. Fill circle: the compounds formed due to covalent bonding are known as covalent compounds. Let us illustrate covalent bonding by taking a few specific examples. 1. Hydrogen, H2. Molecule. Two hydrogen atoms share a pair of electrons between them. Each hydrogen has a single electron in the first shell. Both the electrons are involved in bonding. H plus H arrow H dot H or H, H. Both the hydrogen atoms obtain two electron structure as a result of bonding. It can accommodate a maximum of 2 electrons, since it can get only K shell filled up, for which the maximum capacity is 2 electrons. The two hydrogen atoms are said to be linked through a single bond, since there is one electron pair uniting both the atoms. 2. Oxygen, O2, molecule. Two oxygen atoms share 2 pairs of electrons between them. The electrons of the outermost shell alone are shown here. Remember that electronic arrangement in oxygen atom is 2, 6, and there are 6 electrons in its outer shell. Note that in O2, molecule, both the oxygen atoms obtain 8 electron structure by sharing 2 pairs between them. The 2 pairs of electrons that are found between the 2 atoms are to be counted for both of them, i.e., a double bond is formed between the 2 atoms. 3. Water, H2O, molecule. In water, the oxygen atom shares a pair of electrons with each of the 2 hydrogen atoms. Remember that hydrogen atom can accommodate a maximum of 2 electrons only. Through sharing, the oxygen atom in water molecule has 8 electron structure. Other examples, H2, N2, New Hampshire 3, CH4, etc. You are listening to this audiobook on Audio Learn IGNOU 1.5.4 Isotopes and their applications. All atoms of the same element are exactly alike in almost all properties, but they may differ slightly in their mass. This is because some of the atoms may possess excess neutrons. However, the number of protons and hence the number of electrons remain the same in all the atoms. So we have a situation where, while all the atoms have the same atomic number, some of them show a different mass number than the rest. Such atoms are known as isotopes. Isotopes are atoms of the same element, having the same atomic number, and hence exhibiting the same chemical properties, but different mass number. Examples of isotopes of carbon and chlorine are shown below. Look at the screen. The study of the presence of isotopes can help us in understanding 1. Fractional atomic masses, and 2. Radioactivity. To explain the reason for fractional atomic masses of elements, let us consider the case of chlorine. The 2 isotopes of chlorine with mass numbers 35 and 37 are present in the ratio 7577 is to 2423 for every 10,000 atoms. The atomic mass of chlorine is the average mass of all the 10,000 atoms. Hence, atomic mass of chlorine is a fractional value, namely 35.45. Radioactivity is the property exhibited by certain unstable elements such as uranium, radium, polonium, etc., due to which their atoms spontaneously and continuously disintegrate, giving off rays or radiation. These are naturally occurring radioactive elements. Most of the other elements are non-radioactive, as their atoms are more stable. However, they can be transformed into radioisotopes in the laboratory by special reactions called nuclear reactions. These radioisotopes also spontaneously break down and in the process emit radiation. Many of these radiations find use in the field of medicine for both diagnosis and therapy in certain pathological conditions. The following table, Table 1.4, summarizes the use of some radioisotopes in medicine. Table 1.4, some radioisotopes used in medicine. Radioisotope and their use. Sodium, to follow the course and rate of blood circulation. Phosphorus, in the treatment of leukemia, blood cancer, due to increased white blood cells. Iodine, to diagnose and treat thyroid malfunction, such as goiter. Cobalt, diagnosis and treatment of various types of tumors and cancer. Iron, to determine the formation of red blood cells and their lifespan. Calcium, in the study of formation and metabolism of bone. 1.6 Molecular weight of compounds. From the formula of a compound, molecular weight can be easily calculated once atomic weights of elements are given. For instance, take the compound DaE-FC where D, A and F are names of elements and A, B and C are number of atoms of each, respectively. Molecular weight of a compound equals sum of product of number of atoms of each element present in the compound and its atomic weight. Molecular weight of the compound DaE-FC, A, atomic weight of D, plus B, atomic weight of A, plus C, atomic weight of F. In the examples we are going to discuss now, we consider ionic and covalent compounds in the same way, although, with ionic compounds like sodium chloride, the phrase, formula, unit, is better than the word, molecule. Also, the individual elements exist as icons, although we consider them as atoms only for molecular weight calculation purposes. Example 1. Water, H2O, has 2 hydrogen atoms and 1 oxygen atom and their atomic weights are 1 and 18, respectively. Molecular weight of H2O equals 2 feet atomic weight of hydrogen plus 1 foot atomic weight of oxygen equals 2 feet 1 plus 1 foot 16 equals 18. 2. Molecular weight of sulfuric acid, H2SO4, 2 feet atomic weight of hydrogen, plus 1 foot atomic weight of sulfur, plus 4 feet atomic weight of oxygen, equals 2 feet 1, plus 1 foot 32, plus 4 feet 16, equals 98. 3. Molecular weight of glucose, C6H12O6, equals 6 feet atomic weight of carbon, plus 12 feet atomic weight of hydrogen, plus 6 feet atomic weight of oxygen, equals 6 feet 12, plus 12, 1, plus 6 feet 16, equals 180. 1.7 Summary. A knowledge of chemical substances and principles governing their behavior will help us to appreciate and understand many of our daily activity in a much better way. Chemistry tells us that matter exists as a solid, liquid or gas at specified temperature and pressure conditions. Further, we have seen that, when temperature and pressure are altered, the physical states of matter are interconvertible. Undergoing physical and chemical changes is an important feature of matter. Matter is in the form of element, compound or mixture, and these show varied properties and applications. The discussion in the unit clearly highlights the fact that matter in any form is ultimately made up of atoms of elements. We are also now aware that atoms consist of tiny particles of protons, neutrons and electrons. Atoms combine with each other by transfer or sharing of electrons to become molecules. So, we learn that chemical bonding is the basis of the formation of compounds. Finally, we have seen that atoms can exist as isotopes and that radioisotopes can be prepared from some atoms which can be used in clinical diagnosis and treatment. 1.8 Keywords. Atom. Part of an element that is indivisible by ordinary chemical reactions. Atomic mass is the sum of the masses of protons and neutrons in an atom, as mass of electrons is negligible. Atomic number is the number of protons or electrons in an atom. Biochemistry. Subject concerned with study of matter. Chemical bonding. Process of chemical combination of atoms. Chemical change. Change in matter affecting its composition. Compound. Substance formed by union of two or more elements in a definite proportion by mass. Covalent bonding. Combination of atoms through electron sharing. Electrovalent bonding. Combination of atoms through a transfer of electrons. Element. Building blocks of all matter. Ion. Positively or negatively charged particle. Isotopes. Atoms of an element with identical atomic number but different mass numbers. Mass number is the sum of protons and neutrons in an atom. Matter. Any object with mass and occupying space. Mixture. Substance with varying proportions of elements and or compounds. Orbit, shell. Path traversed by electron around the nucleus of an atom. Oxidation. Addition of oxygen to or removal of hydrogen from substance. Physical change. Change affecting the physical properties and state of matter. Radioactivity. Spontaneous disintegration of atoms of unstable elements giving off radiation. Reduction. Addition of hydrogen to or removal of oxygen from a substance. Valency. Combining power of atoms which is equal to the number of outer shell electrons transferred or shared. Thank you. Subscribe to our channel for more updates, and we will see you with the next chapter.